Hey, Year 12s, thanks for coming along, guys. Okay, so today I'm running through the January 2016 IAL edexcel paper 1. This is for my A-level students. So this will be really handy just to be able to show you what bits, you don't need. There's been a change in specification in 2018, so the Born-Haber cycles have been moved over to A2, so you'll know which ones you can and can't do. I'm just gonna check that this link is working and make sure that my Wi-Fi seems to be still. There we go. It seems to be good quality, which I'm really happy with. I'll move that over to this side and I'll pop out the chat and then I'll close that. At least I'll have the chat there. There we go. It's nice to see that my Wi-Fi seems to be holding up a bit better. I'll also copy the link as well for the YouTube video. Oh, nuts. I'll copy the link to the YouTube video and I'll put it onto the Google Hangout chat so you guys know where it is. Just for reference. Copy the link as well for the YouTube video. Get rid of that. Oh, Winket's here. Lovely to see you, Winket. Thanks for coming along. It's really good to see you. Winkett, I love the fact that you like to watch my different lessons. Like you've even been to some of my year 10 and 11 lessons. I am going to do some exam reviews, Winkett, of some of the A2 papers. They're really hard. I'm not going to lie, the A2 ones are tough. And I'm very aware that, I do need to go through them, though. And it's really good for me as well, especially like the nitrogen chemistry, the azo dye stuff. That's all really tough. So I'll do some of those as well, Winkett, just so you know. I am on it. I'm trying to do as many as I can without annoying my other half too much. Right, I'll get rid of my YouTube video now. Now that the link's on the Year 12 Hangout. Right, let's crack on. We're 2 minutes into the broadcast. Sorry about chatting too long. It's always good to be able to note how long it takes me to run through these papers as well. There's me showing my screen. I'll change my camera over to my clip cam, so to Harry's clip cam. Do you know what, Harry? There's Shazza. Nice to see you, Shazza. Thanks for coming along. Shazza, if you want to have a go at the paper before watching this, you're more than welcome. But if you just want to run through the paper with me, you can pause the video, have a go at the questions and see what the correct answer is. You can do it that way as well. Yeah, Harry, you're going to get a shout out for the rest of my teaching career because of this clip cam. Right, let's crack on, guys. I'll switch my tablet into tablet mode and we can crack on with the paper. Hopefully, this paper is an hour and a half. It'll be really interesting to go through it and see how long it takes me. I will flag up any questions that you're not needing to look at for your mock, but I'll do the paper in its entirety. So it's out of 80 marks. Okay, let me know if there's any... Yeah, Harry, I'm glad you appreciate that. Let me know if there's any issue, guys, on the chat. I know that my tablet does have various idiosyncrasies these days. Yesterday, it stopped letting me write on it because I think it overheated. I've got my little fan set up. I might even plug in my fan just so I know that the battery's not going to die. Because the problem is once I start, you see, I never pick up when things like my fan dies. Right, okay. So, which row in the table shows the number of protons, neutrons, and electrons in a fluoride ion? And that's the key thing, isn't it? It's not a fluorine atom. Everyone will look it up on the periodic table. They got 9 and 18. So what they'll do is, of course, 9 protons, 9 electrons, and then 9 neutrons. Oh, so, hang on. Yeah, 9 neutrons. It's worthwhile me just checking periodic tables. I'm very aware that I should never... And you shouldn't either. I know that you guys start picking up numbers from the periodic table, but it's always worthwhile checking. So fluorine over there with 10 and 19. So 10 neutrons. So what did I put? I put 18. You see, tiny little things like that. So in a fluorine atom, it would be 9 protons, 9 electrons, and 10 neutrons. But this is not a fluorine atom. This is a fluoride ion. What that means is it's gained the additional electron. So we're going to have 9 protons, 10 neutrons, and 10 electrons. So the answer is going to be D. Let's move on. This one, what a lovely question this is. We know in mass spectrometry, when we do the diatomics, we get a series of peaks. So straight off the bat, it's told us that there's 3 isotopes, which means there's going to be a peak at 16. There's going to be a peak at 17. I don't know what the ratios are. It doesn't tell us. Yeah, a peak at 17 and a peak at 18. But that's not what the question is asking us. The question is asking us the number of peaks there would be for the diatomic version, which is when it's in pairs. Now, this is actually a really clever question. So what we can have is, we could have an oxygen 16 bound to an oxygen 16. Yeah, and that's going to have an MR of 32. We can have an oxygen 16 bound to an oxygen 17, which is then going to be one extra, so it's going to be 33. We're going to have an oxygen 16 that could be bound to an oxygen 18, and that's because of the 3 isotopes in it. So that adds on an extra one, so that's going to be 34. Now, I've done all the 16s, but we're also going to be able to get oxygen 17 bound to an oxygen 18. At this point, I know this seems crazy. I'm dropping over to my calculator at this point. I know it seems bonkers, but I think it's very reasonable to do that. Oxygen, oh, I should actually do oxygen 17 bound to oxygen 17 as well. Let's see what I've done. I've done all the 16s bound to everyone else. Now I should do the oxygen 17s bound to everyone else. So 17 plus 17 is 34. I've already got it. Don't need to worry. Then I'll do oxygen 17 bound to an oxygen 16. Already got that one as well, because that's going to be 33. Already got that one as well. So this is 34, but I've already got the 34 here, so I ignore it. This one, of course, drops me at 35. Is that right? Oxygen 17 bound to an oxygen 16. 33, I've already got it. Don't need to worry about it. But then I could have an oxygen 17 bound to an oxygen 18. What's that number? Oxygen 17 plus an 18, which is 35. I've not seen that number before, so this is going to be another one. So I've got a peak here, peak here, peak here, and now a new peak. Now there's no oxygen 19, so I can ignore it. Now what I'll do is I'll do oxygen 18 bound to an oxygen 16. Already got it, 34. Then an oxygen 18 bound to an oxygen 17. Already got it. Already got it, because that's going to be oxygen 18 plus 17 is 35. I've already got that one, yeah, there. But now I could also have an oxygen 18 bonded to an oxygen 18. It's a very interesting game, isn't it? Plus 18, so 36, and I'm done. So I've got 1, 2, 3, 4, 5 peaks. So my answer there is going to be B. It's a clever game, that. Definitely favorite question so far. Good old parts per million. It's always nice to remember that we've got parts per million. Well, the question is, what's my million? So that's my million there. Now, there's 2 ways of tackling this question. So one, you can use the equation, which is parts, which is going to be the small number inside my million. So I'm going to do 0.015 divided by my million, which is that. Yeah, and then I'm going to times it by a million at the end of it. Yeah, that's the equation. The smaller one divided by the thing, as long as the units are the same and they can make it. We'll watch this after having breakfast now, no problem. So if I run that through my equation, because the units are the same, I can do that over 2,000 times by 1 million. Count my zeros. 6 zeros, I've done 7. It's so easy to do. 7.5, so my answer there is B as well. By the way, I'll mark this at the end. I'm doing this as if I'm sitting the paper. So, I'm not infallible for sure. It's definitely something I always like to say to students. It's as good as me doing this practice for everyone else. Right, I've got 10.6 grams of sodium carbonate in 250. Work out the concentration. Number of moles is grams over rams. So I'm going to have to work out what the MR of sodium carbonate is. Sodium is 23.0 on the periodic table. There it is. Never guess. 0.0 times by 2. I'm going to add that to carbon, which is 12.0 times by 1, and oxygen, which is 16.0 times by 3. Let's add that together. 23 plus 23 plus 12 plus 16 times 3. Gives me 106. This is great, because look at the number. It's like 106 with a decimal. So 10.6 over 106 is going to give me 0.1. I'll still run that through my calculator, though. I never trust any head maths. So that's the moles. I'm now putting that into 250 centimeters cubed. So my new equation is number of moles equals C times V over 1,000, because I'm in centimeters cubed. I'm after concentration, so I'm going to reorganize. Times by 1,000 over a volume of 250. So that gives me moles of 0.1 multiplied by 1,000 divided by 250. And I get an answer of 0.4, which is A. Next. So straight away, this is endothermic. We know these graphs from GCSE. We know them well. Yeah, so it's endothermic straight off the bat. So it's either going to be A or C, and that's because the graph's going up. These, of course, are our reactants. These are, of course, our products. So X is reactants, Y is products, and it's endothermic. The answer is C. Moving on. Love this question. So this is actually just a bond data question. So this is burp, reactants minus products. But it's a multiple choice. Now, there's tricks to multiple choice on burp, and I don't like you to actually do it, really, because if you start running the tricks of this, then you'll lose the marks if you're in a long answer. I'll explain the trick. The reason being is usually what you do is you divide this in half, and you say reactants and products. I'm going to smash all of these bonds, yeah, and I'm going to total them up, and then I'm going to smash all of these bonds and total these up, and then one minus the other. Well, because this is multiple choice, we can shorten this. It's not good for the long answer because you will lose the mark. Because would you agree that these bonds here, 4 of the carbon-hydrogen bonds haven't been broken? Yeah, so you can actually shorten this. I'm actually not going to do it. I don't like the shortcut. Students tend to pick up bad habits. So I am going to do this properly. It'll take me a little bit longer. So I'm going to break CH bonds. I'm going to break 4 of them times by 4. Let's write the number underneath that. There's 413. Right? I'm now going to break, so I've broken all of those guys. I'm now going to break 1 CH, so C double bond C. I'm going to break that one there, which is times by 1, and that's 612. And then I'm going to break 1 bromine bond. So I'm going to put a BR bond there times by 1, and that's 193. I will total that up. So 413 times by 4 equals, and the great thing is the others are just times by 1, so plus 612 equals plus 193 equals. So the total there is 2457, 1 mark in your long answer. Right, so there's my total. Now I'm going to smash all of these guys. So I've now got 4, same thing again, 413 times by 4. They're the same bonds, you see. They're the CH bonds. Now I'm going to break a carbon-carbon single bond times by 1. Carbon-carbon single is there at 347. And then I'm going to break 2 carbon-bromine bonds. So carbon-bromine bonds times by 2. Write my data underneath, which is 290. Right, tally it all up. 413 times by 4 plus 347. So easy to get a calculator error on this. 347 plus 290 brackets. 290 times by 2. That gives me a total of 2579. Reactants minus products, which is that's my reactant, that's my products, 2457 minus products 2579 gives me an answer of minus 122. So there's my answer there in black. I'll switch over to black there. So there's B. Lots of B's appearing. Right, next. So now we want to figure out what group in the period this is ionization energies. So we've got 1,000, 2,000, 4,000, 6. Woo-hoo-hoo! There's my jump. I'm in group 4. It's a clever one, that, because they're giving you massive numbers to begin with. And now, of course, they're just looking for this. What we do is we spot where the massive change is. Yeah, and there's a massive jump there. So I'm going to have 4 electrons in the outer energy level. That's going to be in group 4. Maybe could be carbon. Carbon only has 6 electrons. So it could be carbon. Could very possibly be that. Right, next question, really lovely question. So this is ionic radius, 4 sequence of ions, trend in the table. So which diagram shows the trend in ionic radius for the sequence lithium, sodium, potassium, rubidium? Now the great thing is with this is we can do atomic radius. The atomic radius down the group, so lithium has 2 shells. Then sodium, of course, has 3 shells. So what we see is the general trend for the atomic radius gets larger. Then we have the ionic radius. Now, all of these are in group 1, so they have 1 electron in their outer. So they all shrink. It's lithium plus, sodium plus. You get the same trend in the ionic radius as you do in the atomic. So it's going to steadily increase in size. So the answer for that one is A. It's the only one that has a steady increase. Next, which is the diagram that shows the ionic radius is sequenced from, now that's much more interesting. We're now going across a period. So in the across a period, we know that they also get smaller. Sodium, magnesium, aluminium, and silicon. So the atomic radius here as it gets smaller. And the reason for this is they have more protons, and for these two, it's interesting doing this, Oliver will remember this, these two have increased protons but the same shielding. Increased proton number, but same, notice the word same shielding. Yeah, so the electrons will therefore be closer to the nucleus, yeah, greater attraction to the nucleus. Now, if you did that answer for these four, these are interesting because it's a different answer. We've got an increase in proton number and we have similar shielding. Yeah, it still applies, it's still a similar shielding. So the atoms still disappeared, that still decrease in size, closer to the nucleus, increased attraction, but you can't say the word same. The reason being is the outermost electrons in sodium are in the 3s, magnesiums are in the 3s, but now the aluminium is in the 3p, and silicon's in the 3p, so it's similar. Yeah, they're all in the 3s, but we can't say the word same. So in terms of the ions wise, this now becomes +1, this becomes +2, this becomes +3, and well, silicon doesn't really do ionic, which is a bit weird. Yeah, if you did do it, what's it say? It says 4+, it's also going to shrink as well. It's going to be tiny at a 4+. So that's going to be D. They're going to decrease in size. Let's now keep going. Some energy changes involved in so this is now in A2, not part of AS, but it's nice that we can still actually do a lot of this because the understanding of the Born-Haber comes from the Hess cycles that you've done in energetics and AS. Which enthalpy changes represent, right, solid to gas? What are we doing? So we're turning this into atoms. It's what we're actually doing. I know that, so you can also do this as enthalpy of sublimation, but in this case, there's no sublimation on the board. So in this case, we're doing, it's not, electron affinity is the gaining of electrons. Lattice energy is the formation of an ionic lattice. The standard enthalpy of atomization is making atoms, and that's what you do as a gas. And the standard enthalpy of formation is to make an element from there, to make a compound from there, so it can't be D, so the answer is C. Do not, if you, AS kids, if you get that wrong, don't worry about it, ignore it. You can take that off the mark. That is not part of AS chemistry anymore. Which enthalpy does this represent? Oh, so this is the lattice, this is the enthalpy of formation. We're forming it from its elements, 1 mole of a compound from its elements in their standard states. Once again, guys, remove it from your mark scheme. You do not need it. Width 1 is represented by, oh, that's half the bond enthalpy, yeah? Or atomization, we're forming 1 mole of atoms. Same thing, so it's C again. Oh, it's a repeat, isn't that lovely? I like that one a lot. Just to check that I picked the right one. Atomization, cool. Again, ignore all of those from your mark scheme. This one, can I just say, I was really impressed with Harry here. Yeah, this is the same as a Born-Haber. It says work out the value for W. This is your start point. This is your end point. Right, so we're going to go that this way around the cycle. Start at the same place, end at the same place, and flip the arrows where necessary. So I'm going to walk around this way, walk around this way, walk around this way, walk around this way. So my final equation is going to be W equals, this arrow here is with me, so plus brackets minus 437. This one here is now against me because I'm walking in the opposite direction. So against brackets minus 711. This one is also against me, so against brackets minus 349. And then we go brackets. This one is now also against me because I'm walking in this direction. So that says against brackets plus 122. And then this one is also against me. So that's against, yeah, against brackets. What's my value? Plus 419. Let my calculator do, I'm just going to check that number. Let my calculator do all the work. Type that in exactly as I've written it. With me, brackets, minus 437, close brackets. Against me, brackets, minus 711, close brackets. Against me, brackets, minus 349, brackets. Against me, brackets, plus 122, close brackets. Against me, brackets, plus 419, close brackets. And I get an answer of plus 82, which is C. Winner. You can do that as an AS student if you just understand your Hess cycles and applying what you know. Right, once again, still in the Born-Haber section here. This is still part of A2 now. So the lattice energy is the amount of energy released. The amount of energy released when the lattice is being formed. So in this case, it's which one is releasing the most. We know that exothermic is energy being released. So they're actually, technically, if you've got good understanding in bonding, you should actually be able to tackle this, AS students. So calcium fluoride is between a 2+ ion and the tiny F-. Potassium fluoride is now about a K plus and a fluoride ion. Ah, notice the similarity. So that's a fluoride ion. Yeah, and then we've got Ki, K plus and iodide. Iodide is absolutely massive. So the weakest bond here is going to be Ki. So the lowest number out of all of these three is going to be the potassium iodide. The strongest one is going to be the calcium fluoride because it has the highest charge difference. And the fluoride, of course, is very small, so you compare that with the potassium fluoride. So that's going to be the highest. So we need the potassium, we need the calcium fluoride to be the biggest. Calcium fluoride to be the biggest, which it is in these two. Yeah, then we need the potassium iodide to be the lowest, which is then this one. So the answer there is A. Moving on. Clever game there. Right, so this is again still in the Born Harbors. You can remove this one from your mark scheme if you're in AS. The experimental value for the lattice enthalpy is this, and the theoretical value is this. What is the explanation? So what you'll notice is there's a discrepancy between the two of them. This is for my A2 students like Wing Kit, which tells us that there's going to be distortion of the polarization of the negative ion. So the beryllium ion, and by the way, beryllium is tiny. Beryllium on the periodic table, they're saying it's large, it's tiny. It's one of the smallest 2+ ion, and it's in period 2. That's tiny, yeah? And it's going to polarize the fat iodide, yeah? So this is, the beryllium ion is small and polarizes the iodide ion, which is that guy. You never polarize a cation, by the way. Next, this question here is fundamentally incorrect. This really annoyed me. Carbon, diamond, and oxygen both have covalence. We've got diamond, which is giant covalent, yeah? And then we've got oxygen, which is simple covalent, molecular crystal. Yeah, we've got then WIMPs between the van der Waals between the molecules, London dispersion. So diamond is, so it says, what's the best explanation for the higher melting point? Diamond is a solid and oxygen, oxygen is a gas. That's nothing to do with explaining it. Yeah, it says the best reason for the fact. Diamond has a giant atomic, you can't have that, that's not even a thing. You can't have a giant atomic structure. How could you have a giant atom? They meant giant molecular there. There's a fundamental mistake in that question. And oxygen has a simple molecular, that's better. So chances are it's B. Yeah, let's see if the others are garbage. There is a mistake there though, so I'm gonna say that that's incorrect as well. The covalent bond between the carbon atoms in diamond is stronger than that's not true at all. In fact, they're weaker because that's a double bond. So that's garbage. Garbage. And then there is a single covalent bond between the carbon atoms, but a double bond, and well, that's garbage as well. So the answer must be B, even though itself is fundamentally wrong. So edexcel making a mistake there, but it's understandable. Do you know what? It wouldn't actually surprise me if they did that on purpose. Like, that is a classic edexcel to give a question where there's no correct answer, but there's one that's more correct than others. Isn't that irritating? Bugs me that. Next, what is the bonding in ammonium chloride? Oh, I love this question. So ammonium chloride, lovely question. Ammonium is actually a tricky one because there's actually a dative bond in here. Here's ammonium chloride. And then, so we've got Cl. If I'm going to do it properly, yeah, I'd actually draw the chloride with its outermost electrons in it because it's gained the electron. There you go. So we've got covalent, we've got dative, and we've got ionic. We've got everything. We've got the whole shebang. So that's D. Grim. Next, right, one of the isomers of, that's butyrene. Possibly, this is so AS students, you are not doing, you're not having much organic on your mock exam because we haven't started the organic properly yet. I can warn you, you've done organics at GCSE. They can ask a GCSE one. Do watch out. Possible. So this one here, by the way, this is Z-butyrene. Is what that is. That's Z-butyrene because the hydrogens are on the same side. Yeah. And they're giving you cis and trans. So E and Z is one name system, or you can have cis being the same as Z and trans being the same as E. You can do either. So in this case, this one here is going to be a cis isomer. You could also have a trans one as well. So, possible name for this isomer. Oh, okay. So this is Z and cis. So we've got a Z, we've got a cis, so it can be that one or that one, and then a Z. So the answer is B. Again, remove it off the marking, guys. An electrophile, you have not done this either yet, year 12, so ignore this one as well. An electrophile is a species that is an electron pair acceptor. It can accept a pair of electrons to form a covalent bond. It is A. Yeah. Electrophiles, just to point out the bottom ones. Yeah. And by the way, notice that electrophiles are things like HBr. Yeah. Because it's polar, it can accept a pair of electrons to form a covalent bond to the hydrogen, and then that one would break off. Yeah. So that explains A. Yeah. Always has a negative charge. No, that's not true. This still actually has no overall charge. Well, it hasn't. It has a slight charge, but not a full charge, which is what C and D are doing. So ignore them. Right? Alkenes react with hydrogen gas in the presence of hydrogenation. It says this is a clever question. This a 0.2 moles of an alkene reacts with 19.2 dm cubed of hydrogen gas at room temperature and pressure. How many double bonds are there? So this is a mole ratio question. I love this question. Really nice. Now, notice, by the way, edexcel do something really weird, which is, if you do AQA or Cambridge, I'm not entirely 100% sure on Cambridge, but if you do AQA, you never ever use the ideal gas value. We've been given the ideal gas volume there at 24 dm cubed, and that's because AQA teach PV equals nRT. Now, edexcel didn't teach PV equals nRT until 2018. They just stuck with the ideal gas volume, which, by the way, is a ridiculous thing to do. And thank God they changed it. But now edexcel do something really weird, which is like, well, we're going to do both. So they do still use it. So bear that in mind. So the first thing we do is number of moles is V over 24. Now, you use that assuming the volume's in dm cubed, which it is, which that makes it really easy. So the number of moles is going to be 19.2 over 24. If I was given that in centimeters cubed, it'd be over 24,000. Just a reminder from GCSE. So I'm going to quickly work out the moles of hydrogen gas here. So 19.2 over 24 gives me 0.8 moles of hydrogen. Notice I'm being really careful on me writing down what each one does. And then it told me in the question that I had 0.2 moles of an alkene. So I'll put ene. And what you notice is it's in a 4:2 ratio. 4:2 ratio. Sorry, it's in a 4:1 ratio. 4:1 ratio. So the number of double bonds, we needed 4 times. So just to explain what that means, if you had ethene, well, let's do this the way that we should probably do this, and I'll explain why. Let's do this guy. Yeah, let's do pent-1-ene. No geometrical isomerism here, guys, so no EZ in the name. The reason being is this carbon on the double bond has the same group attached twice. You do not need to know this, IS students. I'm just reminding people like Wing Kit who may be watching. So if I now do this with hydrogen gas, we know that the hydrogen gas will break the double bond and go across it. Yeah, so I'll tag those together. Yeah, and this yellow one is going to drop onto here. Yeah, and the double bond breaks. Yeah, so there you go. So what that means is for every double bond, you require 1 hydrogen molecule. So what that means is if I needed 4 hydrogens to every 1 alkene, what that means is that alkene will have had probably got, well, not probably, it definitely had, I'm just doing this for fun, that this molecule doesn't exist. But what this means is there are 4 double bonds, which means I'm going to need, I shouldn't actually do that because it does actually change it just a little bit. I'll do it like this. I'll put them like this. Yeah, I'll get rid of that guy as well. I'll separate them. Yeah, and like that by everyone because that's actually realistic. There we go, there we go, there we go, there we go. And so I'm going to need a hydrogen for here, 1 of those there. I'm going to need a hydrogen for here, 1 there, a hydrogen for here, 1 there, and a hydrogen here. So the 4 moles of hydrogen tells me that there must be 4 double bonds. So it's a clever game, and you don't really need the understanding of the alkene bit. Once you see the ratio, you kind of should recognize that there's probably going to be the number 4 there somewhere. But clever game, though. Clever game. Right, multiple choices done. Into long answer. The relative atomic mass of an element can be determined in a mass spectrometry. You use and define the term. We know that this is going to come up. Yeah, relative. These definitions are very frequent. So this is the average mass of 1 atom. Average mass of 1 atom of an element. You do not need to say, taking into account all of its common isotopes, you don't need to do that because the average has already done it. Yeah, the average mass of one atom of an element, yeah, compared or divided by, whichever one you feel you remember more easily, compared to 1/12 the mass of one atom. That's the most common bit that people forget. 1/12 the mass of one atom of carbon-12 isotope, and you're done. Finished. Next, describe fully how positive ions are formed from gaseous atoms in the mass spectrometry. 2 marks. So this is now explaining ionization. It's actually, yeah, using the electron gun. So we're going to say high energy electrons. I'm allowed to do that. You're not in the exam. Please don't do that. Please stick with the full words. You're not allowed to do it. High energy electrons are fired from an electron gun, an E- gun, electron gun, striking the gaseous atoms, removing the outer, knocking off. I prefer knocking off. From an electron gun, yeah, knocking off the outermost electron. And I will actually give an equation, outermost E-. I'm going to give an equation, so I'm going to go X gas plus the high energy electron. There's the high energy electron from the gun. Yeah, that's going to hit X, and it's going to knock off its electron, which means you get a funny equation. Isn't that odd? It's an odd one, that. It's good to know that. Next. You do not need the electron to have the gaseous symbol because it can't be anything else. Right, a standard, really easy one, this, guys. This is, can I just point out, this is GCSE, not A-level. Yeah? In A-level, what they'd usually give is, they'd give you the relative atomic mass, and they'll scrub somebody and say, work out him, so it's a bit of algebra. But this is just absolutely bog standard GCSE. My year 10s can do this. Yeah, so I'm going to do 84 times that, 86 times that, 87 times that, 88 times that. I'm going to add them all together and divide by 100 because it's a percentage. Now, you need to write it down. You've got to be careful that you can't just do that. Like, you've got to actually show them the maths. So do just take a little bit of time there. Yeah, times by 9.86 plus brackets 87.0 times 7.02 brackets plus 88.0 times 82.56. I'd have to be really careful. If I did that in the exam and I ran off that side, I'm going to lose the mark. So do you notice that I shrank my writing as I went along? So I've made a mistake there, but it's fine for me to do it in an exam review, but I'm just making you aware of that. They will be mean. Yeah, let's run it through the calculator. By the way, I know it's going to be really close to 88. It's going to be slightly lower than 88 because of all the other isotopes being lower. But look, that one is the most abundant. It's going to be like 87.5 or something. It's going to be really close to 88. So 84 times 0.56. I'm actually going to do this exactly on the calculator, exactly as I've written it. Brackets. 84 times 0.56, close brackets, plus 86 times 9.86, close brackets, plus brackets. 87 times 7.02. By the way, very easy to make a calculator error here and type in the wrong number, so bear that in mind. 88 times 82.56, close brackets. Syntax error. See, I've made a calculator error there. 84, open brackets. 84 times 0.56, close brackets, plus brackets. 86 times 9.86. 9.86, yes, close brackets, plus 87 times 7.02. Isn't that interesting? I made it. Oh, I've missed a bracket. See, that's why. So I've made a mistake by not missing it. So 87 times 7.02. Got to watch out for this. It's got to be careful. Plus brackets. I think it's my calculator. I still need to buy myself a new calculator. 88 times 82.56, close brackets. Go. So I'm going to divide that by 100, and I get 87.71. Oh, 3 sig fig, about to lose it. Done. 87.7, finished. Moving on, watch out for the RTFQ, read those. Draw a dot and cross diagram for strontium chloride, show the outermost electrons only. Strontium's in group 2, so this is ionic. So Sr2 plus. Oh, 2 chloride ions. Yeah, that's clever, isn't it? Got to have 2 chloride ions. Yeah, outermost electrons only. So here's 1 chloride ion. You can just put the number 2 in front if you like, by the way, guys. You can do that. It'll allow you to do that, but I wouldn't. I would always draw the two chloride ions. You should. It's good practice. Nice to also have the electron pointing towards it, not that it makes any difference. There you go, 2 marks. Next. A solution of strontium nitrate was prepared by strontium oxide and nitric acid. Write an equation including state symbols. So strontium oxide is going to be, was that strontium chloride? Yeah, okay. Phew. So strontium oxide is going to be SRO, and that's a solid because it's ionic. All acids are aqueous, so HNO3, aqueous. I'm going to form strontium nitrate. Strontium, of course, is a 2+ sign. Nitrate is NO3, 1-. So that's going to be SR, open brackets, NO3, close brackets 2. And, of course, all nitrates are soluble. And I'm going to get water as a byproduct, and I need to balance it. That gains a liquid symbol, and I'm done. Next, a compound, a nice empirical, straight out of GCSE, guys. Nice. So just going to run this. So I've got SR, carbon, and oxygen. I've got 49.9%, 13.7%, 36.4% switch. So percent, this is GCSE, percent to mass, mass to moles, divide by the smallest to find the ratio. And then, of course, multiply if you have fractions. Yeah, so SR, they're doing, oh my God, at A level, they're really doing that? Really? Doesn't half annoy me. Why are they doing that? Drives me nuts. 49.9, you're A-level students, for crying out loud. Stop giving them it. Stop it, losers. 0.56, 770, technically 3 sig fig. 13.7 divided by 12 gives me 1.14, and then 36.4 divided by 16 gives me 2.28. Divide them all by the smallest. 1. Divide them all by the smallest. Divide them all by the smallest. Yeah, I've already got that last one on my calculator, so I'll divide that by the smallest, and I get 3.99, otherwise known as 4, but I'm still going to write down that number. I'm not going to write down 4. That might be a mark in the mark scheme. Watch out for that. So 1.14 divided by 0.57. Be interesting to see the mark scheme. That is exactly 2. So now the final answer, I'm going to write down next to it SRC2O4, and now I'm done. The marks are probably for this set of numbers here. Yeah, for those set of numbers there with the 399 and the final formula being written out. Just letting you know. Next, right, period 3. So formula dotted lines. Write the symbol for the subshell. Complete the configuration for phosphorus. Okay, so where's phosphorus? Oh, there. So 1s2, 2s2. Right, 2p6. 1 in, 1 in, 1 in. Now they go back to pair. Yeah. Then, 3s2. And then 3p3. And that's why they've done it. Now we write underneath that, write the symbols for the subshells. So this is the 2s. This is the 2p. This is the 3s, and this is the 3p. Cool, I like it. The first ionization energy generally increases from left to right across the periodic table. Explain why the first ionization energy of sulfur is lower than phosphorus. Right, so just a reminder of what this question is about. We know that these are going to be on your mocks because they always, well, I haven't actually seen your mock paper yet. So I don't know exactly what's going to be on your mock, but we know that this graph appears all the bloody time, because this is the whole point of atomic structure now. This is A-level. And what we realize is that we have these dips, yeah? So this is sodium, this is magnesium, and then there's a dip to aluminium. The reason being is, for this dip here, is that magnesium's outermost electron is in the 3s subshell. The outermost electrons for aluminium are in the 3p subshell. So there's one mark. And then you say, therefore, a small increase in shielding. Increase in shielding. Increase in shielding. Yeah? And then you say, therefore, further from the nucleus. Outer electron is further from the nucleus, from nuke. Therefore, less energy needed to remove. Yeah, and then this dip's different. Because this dip, by the way, look on the periodic table. The dips, of course, you can then predict, because that first dip is from there to there. Yeah, beryllium to boron, same explanation. 2s, 2p, increased shielding, further from the nucleus, less energy to remove borons than berylliums. Then we can go to the next period down and go, magnesium is in the 3s, aluminium's is in the 3p, increased shielding, further from the nucleus, less energy needed to remove. Then we can go calcium. Calcium's outermost electron is in the 4s, gallium's is in the 4p. There's a high, more that is got further from the nucleus, increased shielding, less energy needed to remove. We can actually just ignore the transition metals. It's a bit crazy, really. And then we then get this dip here between these guys. And the reason for this is because we've got this now becomes to do with these 6 electrons here, which are in the p subshell. So there's gotta be careful here. So these 6, so this is 3p1, there's aluminium, there's silicon, there's phosphorus, there's sulfur. Right, so we've got sulfur is there, but phosphorus has just got these 3. So sulfur is lower to remove the first electron, because we're removing an electron from the same, and this is what I'm going to write down in my box, yeah, sulfur. So we'd say sulfur, phosphorus, sulfur, yeah, sulfur has 2 electrons. 2 electrons, you'd write that in words, 2 electrons in the same 3p orbital. In the same 3p orbital, there is electron-electron repulsion. Therefore, less energy needed to remove. Less energy to remove. We're done. Next, write an equation for the third ionization energy of phosphorus. So the key thing here is to recognize that you're going to go from a 2 plus phosphorus to the 3 plus phosphorus. That's the third ionization energy. I know it seems odd because lots of people tend to put in the 3 and go into the 4, but then that's the 4th ionization energy. You start at the 2 and end at the 3. It's just a little bit backwards. Just got to remember that one. Explain why the first ionization energy of nitrogen is greater than the first ionization energy of phosphorus. Oh, okay. Whoa, that's easy. Because so nitrogen's outermost electron. Oh, my laptop stopped. Come on, there we go. So nitrogen's outermost electron is in the 2p. Phosphorus is in the 3p. Holy moly, that's easy. So you go nitrogen's, should be doing this in black really, so I'm marking in red. Nitrogen's outer E minus, you'd write this down properly in your exam. Nitrogen's outer electron is in the 2p subshell. 2p subshell. And phosphorus outer electron is in the 3p subshell. Oh, increased shielding. Increased shielding. Shielding in phosphorus. In phosphorus. Now, one of the things I keep saying to students is you cannot say increased shielding without the distance. Those two now are tied together. They are banked together. You can't separate them. Increased shielding of phosphorus, so outer electron, so outer E minus, is further from nucleus. Further from nucleus, less energy needed to remove. Less energy. Less energy to remove phosphorus outer E minus. We're done. Draw a dot and cross diagram for a molecule of nitrogen. Good GCSE again, but it's very high level GCSE, like level 8 this, because it's a triple bond. Always start with the sticks. So we know nitrogen makes 3 bonds, it's going to make 3 to itself. So we draw your circles. Can I just say, I know that some students get taught not to use the circles. Please don't. Please don't. Include your circles. The reason why is there have been, if you have a really complicated dot and cross diagram, I should find an example. A student did it recently. If you've got a really complicated dot and cross, it can become confusing as to where the electrons are, and you can lose marks on it. So just use the circles. Right, solid white phosphorus exists as a P4 molecule. Calculate the number of molecules in this many grams of phosphorus. Okay, so that's nice, number of molecules. So this is absolutely bog standard. I was expecting it to say atoms, in which case you'd have to do a multiplier of 4 to break down the molecule into atoms, but this is just absolutely bog standard. So we're just going to go number of moles as grams over grams. We need to get to moles first. So we've got 24.8 grams of it. Now we need to know the weight of a phosphorus molecule. So phosphorus weighs 31. Don't know why my pen's not working on it. Oh, it's because it's on that. Weighs 31. So 31 implies this is a really bad habit. I'm mentioning this on purpose, year 12. 31 times 4, that's lost you a mark. Please don't do it. It's not allowed. Write it somewhere bloody else and give me the real number. That's a bloody mark. Stop doing it. 31 times 4, there is 124.0. That's the mark. Not for that. Watch it. So grams of grams, 24.8 divided by 124.0, and I get 0.2 moles of phosphorus molecules. And then it tells me Avogadro's constant, multiply that by Avo, and I'm done. Multiply that, so my times 6.02. 02, exponential 23. Go. And I get a final answer of 1.204 times 10 to the 23 molecules. If I had atoms, I would now multiply that by 4 because each molecule contains 4 atoms. Next, compound X has a molecular. Draw the displayed formula of 3 structural isomers. This is GCSE. My year 10s can do this. I'd expected you to have had a go. So the first one you're going to draw is the straight chain. Of course you are. Let's give it a straight chain. First one, straight chain. Just standard pentane. Name this. And it wants displayed formula, so all bonds must be shown. You can't draw skeletal. Yeah. Now I'm going to add a branch. Break off a carbon and put it on as a branch. Can't go on the end, because otherwise it's exactly the same thing, but with a bend in it. Yeah, very common mistake that. Lots of students put it here. That's the same, because it's still 5 in a row. It's just kinky. So please remember to put it in a carbon. I'm not going to bother with my hydrogens in this case, because I'm doing an exam review, but these are all H's. All of these are the end of the H's. Now I'm going to add my second branch. Yeah, because I can't do a position. Oh, got to do a second branch. Yeah, there we go. Because if I move this to here, that's the same thing. I'm just going to read it from that direction. Yeah. So I'm now going to add a second branch, which is 2,2-dimethyl propane. There you go, and I'm done. Next, C5H12 reacts with chlorine to form a mixture. Classify this type of mechanism. This is FRS. Free radical. You can delete this one off your marks. Free radical substitution. That's what that's called. Class the type and class the type and mechanism. Reacts with a mixture of products. Classify the type and mechanism. It's just free radical substitution. So just to tell you, by the way, that's really interesting, because the mechanism is free radical. That's the species. The type is substitution. No. The mechanism is free radical and the type is substitution. That's really interesting, guys. I don't like that. It's going to be interesting to look at the mark scheme for that one. That's the right answer, by the way. I just don't know which way around they want it. Yeah. Really weird, that. It's 2 marks. I'm going to put free radical substitution stroke chlorination. Be interesting to see if they dock me for that. Don't see why they would. Write an equation for the 2 propagate. This is now, guys, for my ASs who are preparing for their mock, you do not need to be able to do these questions, because these are now, you can do all the energetics ones, and I'm going to continue doing it, but it's just nice for me to say, do not worry about these. You do not need to know them, but I would complete it anyway. Write the equation for two propagation steps for this mechanism. Use the molecular formula in the first equation. So C5H12 plus, this is a propagation, so a free radical goes in, and then a free radical comes out. I form HCl and C5H11 and the dots on the C. Put it back in, C5H11, dot on the C, plus chlorine. In the second propagation step, you always put in a chlorine. And that's going to form C5H11Cl plus Cl dot on the Cl. There we go, 2 marks. Write the equation for 1 termination step. Use curly arrows are not required. Any termination? Okay. So I'm going to do C5H11 dot on the C, any termination step. So I'm going to put the dots there, and I then form C5H11Cl2. The terminations have 2 free radicals going in. Right, now, of course, we're getting into this is now for my AS students. This is absolutely on the ball for you guys. An experiment was carried out to determine the enthalpy change of combustion of pentane. It's 100 grams of water, and they've even given you the equation. This will not be given to you from now on from 2018. It shouldn't be given to you at A level anyway. But it says calculate the energy transferred in kilojoules. So we're going to go Q equals MC delta T. Right, so the mass is the mass of water. So 100 multiplied by 4.18 multiplied by the temperature change. The temperature rise was for 114.5. That's going to spit me out in joules. So I've then got to remember to divide by 1,000. 100 multiplied by 4.18 multiplied by 14.5. Go. That gives me 6,061. Yeah, and now that's joules. So now I need to go divide by 1,000. So my energy transferred is 6.061 kilojoules. I'm done. Calculate the number of moles of X used in the experiment. Well, I'm getting loads of bloody messages now, which is really irritating. This will be for my year child going, oh, what's going on, Mr. Duncan? Why are you doing a webinar? You didn't tell us. Okay, it's fine. So, how many moles of X? So he burnt that many grams of X. Yeah, combustion of X. C5, it's weird the fact that they're doing that. So grams over rams, this is just number of moles. Number of moles was 0.144 grams over pentane, the MR of pentane, C5H12. So that's going to be 12 times 5 plus 12. So it's over 72.0. Don't forget the 0.0 at A level. 0.144 over 72.0 gives me 2 equals 2 times, I'm going to do shift eng. It's going to give me 0.002 moles of X. Thank you very much. Calculate the enthalpy change. So delta H equals Q over N. And the Q must be in kilojoules. And this is the moles of our reactant. So therefore, it's going to be delta H equals Q, which was 6.061 divided by moles of 0.002. Don't forget this was an exothermic reaction because the temperature went up, so you've got to flip the sign at the end. 0.061 divided by 0.002. Loads of calculator errors, by the way, that I've been seeing recently. 3,031 kilojoules per mole. And I don't forget to make it negative. You're done. Next, the data book values for the enthalpy of combustion are these 3. The experimental value, and see, is very different from these values. Give 2 reasons other than heat loss for the large difference. This was combustion. So number 1, yeah, incomplete combustion of pentane. Definitely. Yeah, the next one, you can't say heat loss. Evaporation, is there a diagram for this? No diagram. You could say evaporation of the fuel. I think that's probably a good one here. You could say evaporation of the water. Yeah, what was the temperature rise? The temperature rise was 14.5. It's not very particularly high. The heat capacity of the equipment is not exactly 4 because you're heating other objects. Yeah, heating the metal which contains the beaker. Yeah, all that jazz. I'm going to pick one now. I know I've got the top answer, but whether or not I get the next one as being in the top 2 it's the large difference. Yeah, I'm going to say, can't say heat loss. Incorrect heat capacity. Heat capacity. Since I'm going to give clarity on this, since heating not just water, but calorimeter, Bunsen, calorimeter, tripod, gauze, and not just water. I'm going to put that one. Yeah. Explain why it's not possible to deduce which of the isomers X by comparing their experimental values with the data book. Oh. The data book value for the enthalpy of combustion of the three structural isomers. Oh, they're all really similar. Oh my God. Really similar. How could you tell? Explain why it is not possible to use which of the isomers is X. Oh, because our X is so different to all three of those that you really can't, like the difference, as that 1 mark, the experimental value, that's the first. So guys, I'm going to flag these. These are ones of interest for me so far. Boom and booming. Like these questions. The experimental value is very different from all data book values for all three isomers. No clear match to any of them. I think that's very reasonable. That's one I'm interested in, like that. Next. Good old Hess cycle. Right. The standard, and I'm not bothered to read the question. Standard enthalpy change for the formation. So I'm going to make this from its elements. Harry, I looked at your paper. You got this wrong. So I'm going to make that from its elements. So in order to do that, I need hydrogen gas. I need carbon as a solid. Yeah, right. I now need then, so that would be the formation of these guys. Yeah, and I'm making there's only one here and only one here. So I can write that value onto that, minus 173. Yeah, now look at this. This is really clever. The combustion of hydrogen, well, the combustion of hydrogen is to make water, which is over there. So now I need to balance this. I'm going to need 6 hydrogens for that. Well, I need 6 hydrogens for that as well to get the C12. It's going to balance out. Yeah, and then I'm going to also need oxygen so the oxygen to balance the cycle. So I'm going to need 8 O2s. And what you realize is that the enthalpy of formation here, yeah, and the enthalpy that can be used in the same cycle, because the formation of the elements creates him. So the formation of the elements creates him, but then the combustion of the elements also forms these. So it's a rather clever question, this. Really, really lovely. And then it also gives the combustion of carbon, which is great. Delta HC, this can be the carbon one, this can be hydrogen, this can be the carbon, there we go. And now just input your data. Now this one's much more important, because the reason why I don't have to multiply this value here is because the standard enthalpy change makes 1 and we're only making 1 here. But now we're making 6 carbon dioxides. Well, the standard enthalpy of combustion will make 1 CO2. So I have to multiply this by 5. And this is making 6 waters, so this has to be multiplied by 6. So the enthalpy of hydrogen, which is enthalpy, I've got to be careful here with my data, times 5 is carbon. So this is not I'm making a mistake there. That's the carbon, and this is the hydrogen. I've flipped over the numbers, not that it matters. But I now need to input my numbers on here. So this is the enthalpy of combustion of carbon, which is going to be minus 393.5. Then the enthalpy of combustion of hydrogen, which is minus 285.8. Right, then I can create my cycle. This way equals this way. So this one is against me. So my answer, my question mark, equals, so my against brackets minus 173 times 1. This one is with me. Yeah, it's with me. So plus, with me, plus 5 times minus 393.5. Got to be careful there. Easily done. 0.5, close brackets. And then this one is with me as well. So with me, brackets, 6 times minus 285.8. Right. Run that through my calculator, exactly as it is. Minus, turn my calculator on, minus. So against me, brackets, minus 173, close brackets. With me, close brackets, 5 times minus 393.5, close brackets. With me, brackets, 6 times. Oh, got to be careful, forgot my minus. 6 times minus 285.8, close brackets, go. And I get an answer of minus 3509 kilojoules per mole. That is insanely exothermic, but that makes total sense. I am burning pentane. This is a combustion. So, lots of energy. I'm done. Moving on. Okay, once again, not going to be on your paper. Give the molecular formula, but you can tackle this one. This is GCSE year 12, so it could be on your paper. C, 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 and C. So that is 1, 2, 3, 4, 5, 6, 7. So the molecular formula, C7H. Right, now I'm going to count my H's. So 1, 2, 3, 4, 5, 6. None on it. 7, 8, 9, 10, 11, 12, 13, 14. That makes total sense. One double bond, it's an alkene, I'm happy. Explain why the alkene exhibits geometrical isomerism. Because both carbon atoms involved in the double bond, involved in the carbon-carbon double bond. Let's see what I've done there. Double bond, have two different groups attached, so they can have different arrangements in space. I like it. Same molecular formula, but different arrangements in space. Yeah, it's a clever question. Give the reagents needed for reaction number 1. Oh, bromine water. It's clever, isn't it? You'll learn that, guys, when that's not GCSE, it's A-level, because with bromine water with GCSE, you learn that it does that. In reality, it doesn't. Sorry, you did fib. Identify by name or formula the organic product of A in reaction 2. So potassium permanganate and dilute sulfuric acid, organic problem, organic compound. Oh, that's an ene. Oh God, I think we're going to form a diol. Potassium permanganate. I thought it was the other way around, but no, it mustn't be. Dilute sulfuric I'm pretty sure that's what it is. I'm pretty sure that's a diol. Organic product 2 there. Oh, by name or formula. Oh, name or formula. So you're going to add, what's going to happen here, guys, is you add all groups across the double bond, and you have to just learn this transformation. Really weird transformation. So this is going to be 1, 2, propane. Ooh, propane 1, 2 diol. Wow. Propane with the E. 1, 2 diol. Blimey. So that's by name or by formula. Yeah. I'd probably have gone for formula if I'd actually been you. With potassium permanganate and sulfur, I'm pretty sure you form a diol. State the change in color you would see in reaction 2 if it was carried out. I think it goes from purple to colorless. Yeah. Purple to colorless. The reason, if you're interested why, wing kit, if you're watching this, the reason being, of course, is the purple is the MnO4- sign. That's dark purple. And it's becoming MnO2. It's being reduced, and that's colorless. Yeah, this is dark purple, and this is colorless. Yeah, so I should remember that. Balance the half equations. Give the mechanism for reaction 3. Use curly arrows and show any dipoles and lone pairs. What are we doing? Reaction 3, ene to 2-bromopropane. I like it. Good old electrophilic addition. So we've got propene. There we go. Or I'm going to do this properly, like I'm in a real exam. This is with HBr. So the H will go pointing towards it. Find your deltas. Yeah, we're going to have a touch that bond going to the H. That bond breaks away. Product. Double bond is broken. And is it showing the major pathway? Oh, it put the bromine on the middle one. Notice, look, that's clever, that. You can't choose. The bromine is on the middle carbon, so it's pushing you in the direction of that particular. We know that we're going to get major minor products here, and it's pushing you into the major pathway. Yeah, so the carbocation is there, and then the bromide ion, yeah, with its lone pair, now hops on. We're done. Nice game, that. Next. Draw butyrene polymerizes to form polybutyrene. Draw a section of the polymer showing 2 repeating units. So butyrene, to do polymers, this is GCSE technically, by the way. You can do this year 12. It's GCSE, so that's butyrene. Just to show you what I've done here, I've straightened it out. Sorry, I've taken the straight one and I've bent it to make the double bond like this. And there's a reason for that, because when it polymerizes, we realize the double bond breaks open. Yeah? And it wants 2 repeating units. Be very careful, by the way, when I do that, because if you do this, you've lost that mark there now, because that bond has to go to the carbon. Yeah, be very wary of doing my trick here. I don't actually like it. 2 repeating units. Yeah, there we go. CH3 and then CH3, and I'm done. There's 2 repeating units of polybutyrene. And we're done. Next, no brackets or N required actually now. Next, calculate the percentage atom economy for the mass of, I like this one, just atom economy for the production of cyclohexene. So we know that the percentage atom eco is wanted over total times 100. Right, and by the way, I like to do total out because you've already done half of it. So what's the molecular weight of cyclohexene? So I have got, this is going to be interesting, this, carbon, 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 carbon. So I've got C6H, now I've got to be really careful, 1, 2, 1, 2, 1, 2, 1, 2, 1, and 1. So it's 10, it's a weird number. So that's cyclohexene, work out the MR of that guy, 12 times 6 plus 10, 82, 82.0 over, so that is what we wanted over the total out. Well, we've got cyclohexene already, just add on 1 water, so add on 18. So that's over 100. Oh, look at that, times 100. That's going to be clever, that. People are going to forget that, and you're going to lose the mark. Anyway, it's 82%. There we go. Calculate the percentage yield if 10.2 grams of cyclohexanol produces 6.1 grams of cyclohexene. Right, okay, that's quite clever. So this is a reacting mass first. You've got to do the reacting mass question first. I think this is the last question. Yeah, total. This is the total for section B, total for paper. This is going to bring us to the end of our webinar. So I've got to do a reacting mass first. So calculate the percentage of 10 point, so I've put in 10.2 grams of cyclohexanol. So I need to work out what the theoretical yield is. Yeah, so I'm going to go number of moles of cyclohexanol, 10.2 grams over the MR of that guy. Right, so I'm going to work out the MR. So once again, 6 carbons. So 6 carbons, I'm going to write this over here, 6 carbons. How many H's? I'm going to put these in red. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and 1, and another. So 2, 4, 6, 8, 10, 12, and 1 oxygen. So there's cyclohexanol. So 12 times 6 plus 12 plus 16. MR is exactly 100. Of course it is. It's the same as the MR out. How fascinating. So the number of moles there is just 10.2 over 100, which is just going to be 0.102. I still don't have my calculator. Don't want to trust myself with moving a decimal place. It's worthwhile doing this. I know it seems mad. Like, IB have a non-calculator paper, I believe, which is very fun to do. You kind of take approximations for everything, and it can be done. It's not as bad as you think. So this is the moles of cyclohexanol. So the ratio now is a 1-to-1. Ratio 1-to-1. So I would therefore make 0.102 moles of cyclohexene. Yeah, of C6H10. Well, now I can work out the mass of that. So number of moles is grams over rams, and I want grams. Reorganize. Moles times by rams will give me grams. Input my numbers. 0.102 of that person. Yeah, it was that, wasn't it? Yeah. So I now need to work out the MR of it, which I have already done. It was 82. So I'm going to multiply that by 82.0. Multiply that by 82.0. And I get a mass. I should have made 8.364 grams of it. How much did I make? I made 6.15. 6.15, was it 1.5? 6.15 over 8.364 times 100 will give me the percentage yield. I've already got that number on my calculator, so I will keep it divided by answer times 100 and I get 73.5% of my papers done. Right, how long did it take me? Interesting, isn't it? So that's 1 hour and 9 minutes. Very reasonable in terms of length of time, that, guys. Now I need to, of course, mark it, because there are some very interesting questions there that I'm quite excited to see if I get right. So what I'm going to do is I'm going to split my paper in half. I'm still sharing my screen with you guys. I think I have the mark scheme somewhere. Maybe I don't. Mark scheme. I think I might need to download that one. So if I go to PMT, I'm trying to. Oh, I think my mouse has gone to sleep. Oh, sorry, mouse is not. There you go. It's back. So if I go now, January IAL paper 1 mark scheme. There's a couple of questions here that are genuinely interesting for me. Good for him. Right, up to the top. I'm excited. Let's see if I never expect to get 100%. I'd never expect that. Yeah, A-level's hard. I mean, A2, I'm guaranteed not to get full marks, but it's all a game. You learn to adapt and make improvements. So first one, D, I like it. Next one, B, I'm on it. Next one, B, I'm on it. Next one, A, I'm on it. Next one, 5, C, I'm on it. 6, B, yeah. 7, C, yeah. 8, A, 8, B, D. 9, 9A was C. 9B was D. 9C was C. Doing well so far. Oh, 10C, nailed it. Question 11A. Question 12B. Question 13B. Oh, that was the one that I didn't like. Question 14D. Oof, good. Question 15B. Question 16A. Am I going to get 100% on the multiple choice? Yay, winner. Oh, it's always nice to have that. I don't expect it, though. Just remember that. I do not expect those things to happen. You just expect them to get good marks. You know this. Right, weighted mean, allow average mass, atomic mass, second mark of atoms of an element, yet divided by 3 marks, 1/12 the mass. I will take all 3 of those. Thank you very much. Next one. Beam after high energy electrons bombard, hit, fired, striking, knock off, liberates electrons. I like it. Yeah. Cool. Take it. Take it. Next. 87.7. 3 sig fig. Boom and boom. I'll take it. Thank you very much. Next. Oh no. I missed a question. And there you go, folks. I missed one. There you go. Easily done. Which block in the periodic table is strontium found? The S. I missed one. There you go. Told you I wouldn't get 100%, and no one even caught it. Look at that. No one even mentioned it. I wonder how many people are watching. Am I down to 0? It could very well be at 0 at this point. Am I bothered? Am I bothered? 3 people watching. Yeah, it's all right. I missed it. There you go. Not 100% for Mr. Duncan. Yeah, and it is the S block. I'm not going to get my say. I'm going to say, by the way, this is be careful. Be careful. Yeah, don't skip questions. Yeah, take your time. I clearly rushed it, skipped it. There we go. There we go. So straight away. Oh, do I miss the mark for not showing the outer electrons in strontium? Correct dot and cross diagram. First mark, correct dot and cross diagram with +2 charges and -1 charges on the chloride. Fine, 1 mark. Second mark, ratio 1:2. Allow this shown as in chlorides, ions. Ignore any inner shell electrons. Isn't that fascinating? Allow no electrons or 8 electrons for the shell of strontium. Woo! Take it. Boom, boom. Love it. Next one. I'll take it. I'll take it. Balanced equation. All state symbols. Okay. I like it. Next. I told you what the numbers would be for. They allow 4. It's irritating, isn't it? And then formula at the end. There we go. So I'll take all 3 of those. Winner. Next. There we go. Yeah, I'll have that one too. And the 3 Ps. Oh, labeled correct. Or ignore numbers or subscripts. Okay, so I didn't need. God, it would be a nightmare. Oh, write down the symbols of for the subshells of the dot on the dotted line. I am correct. It's okay. You don't need, if it was for all the orbitals, there'd be individual lines for each of them. That's when you need 2px, 2pz, 2py. Yeah. Anyway, next. So first mark, there are 2 electrons in the same orbital, 3p orbital. Tick. Next mark, there is repulsion. Yeah, I like it. Electron-electron repulsion, less energy to remove. Next, phosphorus going to the 3rd ionization energy with gaseous symbols. Well done. It's easy to miss the gaseous symbols. Yeah, there you go. Nitrogen has fewer energy or fewer shells than P. Should be energy levels. But outermost electron in the 2p. Yeah. Mention molecules lower atomic number. Ignore. That's fine. Yeah. Outermost electrons is in a shell closer to the nucleus. Increased shielding. Yeah. Outermost electron less shielding. There you go. The shielding is a mark. Yeah. And then so outermost is held more strongly. Less energy. Oh, I think I lost one there, guys. And I should have put it. I think I even said it when I was writing it, but I'll definitely add that in. Yeah. So outermost electron is in the 2p, phosphorus in the 3p. You do get a mark. Increased shielding, further from the nucleus, less energy, greater attraction to the nucleus. That with greater attraction because it's closer. Yeah. To nuke. Add that in. I'll take a mark off me there. I'll definitely give myself 2, but not 3. Yeah, there we go. Dot and cross diagram. Please use your circles. Next. 0.2. Final answer, 1.0 times 10 to minus 3. There we go. I like it. Then our 3 diagrams. Straight branch, double branch. I like it. I was interested by this one. There you go. So the type is free radical. And the mechanism is, I disagree. It's garbage. Don't like it. Don't like it, but I get all the marks for this. Yeah, ignore chlorination. Next, my equations are all okay. Yeah. Terminations, I like it. That's not a real termination, please. The CL dot is not a real termination. This says allow any, but that's not a good one to ever learn. Ignore that, please. So 6,100. Right, allow. The question says specifically, give it in kilojoules. Whatever. Next one, 2 times 10 to the minus 3. Final answer, and there's going to be the sign for the negative. Yeah, correct sign. Yeah, minus 3. Yeah, I like it. Times 10 to 6 joules. It's weird. Yeah, I can have both marks for that, showing the maths behind it. Right, was interested by these 2. Incomplete combustion. We knew that would be the top one. Second mark. Damn it, evaporation. Evaporation of the alkane or fuel. Allow alkanes volatile. Heat capacity, heat absorbed by container apparatus was not included. Yes. Incorrect heat since heating, not just the water. I'll take it. Oof, was in the lab. The ignore one. Look at all they ignore the evaporation of water. I thought about it. Thank you very much. I'll take it. The experimental error are greater than the differences in the data. Or the experimental is much lower than all the data book values. Yay. I'll take it. But the experimental errors, they didn't ask us to do the errors though. This one was an awesome hair cycle. Did enjoy that one. 3509, thank you very much. Given the calculation and sewing the cycle. Winner 4 marks too. I'll take all 4 of those. Balanced cycle. C7H14. Oh, I liked this one. So restricted rotation. Allow no rotation of the double bond. I lost it. Damn it. It's asking for why. Explain why the alkane. Second mark, 2 different groups on each of the carbon atoms. So I gain 1. CC double bond can't rotate. Definitely lost that mark. Yeah. Ooh, why can I smell burning? Don't think it's my laptop. Is it outside? Okay. Bromine water, I'll take it. Propane 1,2-diol, yes, winner. I remembered. Purple to colorless, Yay! Purple to pink, or it should be colorless really. Mechanism. Boom, boom, boom. I'll take it. Thank you very much. 4 marks. Ha ha! Love it. Is there? Like, is it in the cardboard? Oh. Oh, who knows what the hell they are doing. Can go up or down, allow groups below the chain or above the chain. Take it. Right, loads of horrible maths. 82%, nailed it. And then 73.5%. There you go. Perfect. We're done. Tick and tick. It's actually, yeah, it's actually the 8 thingy gram bit, isn't it? Moles of cyclohexene. We did that. What? Oh, have I not gone down to I'm on the last question? D2. Yeah. First mark, moles. Oh, yeah. First mark is the moles. It's there. Yeah. And then multiplying that by my thing there to give me there's the mass. 82. Well, okay. They've just skipped it. That's irritating, isn't it? And then multiplying that by, oh, that's strange. Have I got the wrong answer? That's weird. Don't like that. My method's better, which is this one. Yeah, which is the bottom one. Yeah, 73.5. Yeah, it's fine. Anyway, great questions. Nice paper. I definitely had a couple of, I told you I'd never get 100%. It was close. I did pretty well. I'm pretty happy with that. I'm going to leave you guys be for the day now. Let's bring that back to here. Stop sharing. Bring it back to you guys. Right, guys, I hope you found it useful. And now what I'm going to do is I'm going to ask you guys now. Tomorrow, I'm going to do the IAL January 2016 paper 2. So if you can now all have a go at the paper 2, and tomorrow at 10 a.m., I will do that one. I hope you guys all have a lovely rest of your day. Take care, guys. See you later.